Hello everyone, welcome back to Mana CS Classroom. In previous video, we discussed what a data structure is and why data structures are important. Today we are going to answer a very interesting question. We have arrays, we have linked lists, we have stacks, queues, we have trees and graphs. Why do we have so many different data structures? Can a single data structure solve every problem? The answer is no. Different applications require different ways of organizing data. That is why data structures are classified into different categories. Let us understand that classification. This is the complete classification of data structures. At the highest level, data structures are divided into two categories: primitive data structures and non-primitive data structures. Non-primitive data structures are further classified into linear data structures and non-linear data structures. So throughout this course, almost every data structure we study will belong to one of these categories. Let's start with primitive data structures. Primitive data structures are the basic data types directly supported by programming language. Examples include integer, float, character, and boolean. For example, int age, char grade, float salary. These are the basic building blocks used to construct more complex data structures. So think of them as individual small bricks which help us to build complex buildings. When we combine primitive data types in a structured manner, we get non-primitive data structures. Examples include arrays, linked lists, stacks, queues, trees, and graphs. These data structures help us manage large volumes of data efficiently. In fact, most real-world software applications use these data structures internally. The first category of non-primitive data structure is linear data structures. In a linear data structure, elements are arranged sequentially. One element follows another element. Examples include array, linked list, stack, queue. A simple real-world example is a queue at a ticket counter. People stand one after another in a sequence. Similarly, elements in linear data structure maintain sequential relationship. The second category is nonlinear data structures. Here elements are not arranged sequentially. Instead, they form hierarchical structures or network-like relationships. Examples include trees and graphs. These structures are extremely useful when relationships between elements become more complex. So let's briefly discuss each data structure. First, array. An array is a collection of similar data elements. All elements in an array must have the same data type. For example, int marks of 10. This statement creates an array capable of storing 10 integer elements, 10 integer values. One important feature of arrays is that elements are stored in consecutive memory locations. Because of this, accessing an element is very fast. Although arrays are simple and efficient, they have some limitations. The size of an array is fixed. Insertion and deletion operations are also expensive because elements may need to be shifted. Suppose let us assume Ramu and Rajesh ఇద్దరు పక్క పక్కన కూర్చున్నారు. ఓకే, మధ్యలోకి ఎవరైనా వెళ్ళి ఇన్సర్ట్ అవ్వాలనుకుందాం. సో రాజేష్ అటువైపు షిఫ్ట్ అయితే మధ్యలో ఒక ప్లేస్ వస్తుంది, అది కూడా అటువైపు ప్లేస్ ఖాళీగా ఉంటే. ఓకే, సో దెన్ the middle element, an element can be inserted in the middle. So these limitations led to the development of another structure called linked list. Okay, so whenever one data structure shows limitations, computer scientists try to design another data structure to overcome them. So a linked list is a dynamic data structure. It consists of nodes. Every node contains two parts. First part stores data. Second part stores the address of the next node. Unlike arrays, nodes need not be stored in consecutive memory locations. This makes insertion and deletion much easier. So the major advantage of linked list is flexibility. New nodes can be added whenever required. Existing nodes can be removed easily. However, searching takes more time because we must move from node to node. So next comes stack. A stack follows the LIFO principle, last in first out. The last element inserted into the stack is the first element removed. So think about a stack of books. A book placed last on top is the first book removed. So that is exactly how a stack works. In a stack, all elements, all insertions and deletions happen only at one end called top. So this makes stack operations very efficient. Stacks are widely used in function calls, recursion, expression evaluation, and undo operations. A queue follows the FIFO principle, first in first out. The first element inserted is the first element removed. A queue at a ticket counter is a perfect example. A person who arrives first gets served first. Insertion takes place at the rear. Suppose let us assume 5 people are standing in line. Okay, let us assume these 5 numbers are 5 persons. If a new person wants to join the queue, where he joins at the back side, right? We call it as rear end. And if a person who is already served may leave the line from the front side. So ఇది టికెట్ కౌంటర్ అనుకోండి. ఒక 5 persons are standing in the ticket counter line. సో ఫస్ట్ ఫ్రంట్ ఉన్న వాళ్ళకి టికెట్ ఇచ్చేసాము. సో ఫ్రంట్ నుంచి వెళ్ళిపోతాడు కదా, హీ లీవ్స్ ద లైన్, హీ లీవ్స్ ద క్యూ. ఇంకొక కొత్త పర్సన్ జాయిన్ అవుతున్నాడు టికెట్ తీసుకోవడానికి. ఎక్కడ జాయిన్ అవుతాడు? బ్యాక్ సైడ్ జాయిన్ అవుతాడు. సో ఆల్ ఇన్సర్షన్స్ హ్యాపెన్ ఎట్ రేర్ సైడ్ అండ్ ఆల్ డిలీషన్స్ టేక్ ప్లేస్ ఎట్ ఫ్రంట్ సైడ్. Queues are extensively used in CPU scheduling, printer scheduling, and operating systems. Now let's move to non-linear data structures. A tree is a hierarchical structure. A tree starts with a root node. From the root node, child nodes are connected. A common example is an organizational hierarchy. Principal, HOD, faculty, students. So this naturally forms a tree. So here you can see a simple binary tree. In a binary tree, each node can have at most 2 children. So A has 2 children, right? So when a node has 2 branches, we call those 2 as children. So any node can have at most 2 children. That tree is called as binary tree. Trees provide efficient searching, insertion and deletion operations. The final data structure in our overview is graph. A graph consists of vertices and edges. Vertices represent entities. In the diagram you can see the vertices are A, B, C, D. Edges represent relationships between those entities. Unlike trees, graphs do not have a root node. Any node can be connected to any other node. There are no superiors and there are no parent and child relationship here. All are equal, peer-to-peer connection. So here you can see A is connected to B as well as D. C is connected to D as well as B. B is connected to A and D. So A, B, C, D are called as vertices, and the lines that are connecting these vertices are called as edges. Examples include Google Maps, social networks, computer networks, recommendation systems. In fact, modern recommendation systems such as Netflix and Amazon heavily use these graph relationships. So let us summarize today's discussion. Data structures are classified into primitive and non-primitive data structures. Non-primitive data structures are further classified into linear and non-linear structures. We also got a brief introduction to arrays, linked lists, stacks, queues, trees and graphs. In the upcoming videos, we will study each of these data structures in detail. Thank you for watching. See you in the next class. Do not forget to subscribe to Mana CS Classroom. Thank you.